So it's again from 7-6 onward. 7-6, 7-7. That was the stuff on parabolas, right? Or quadratic functions. Then 5-6, 5-7, 5-8, and 5-9. Okay? Where do you want to start?
7-6.
Older stuff? Look at that first?
Yeah.
Okay. 7-6. What was 7-6? There were two things in 7-6 we looked at. Go ahead.
Quadratic function.
Quadratic functions in general. In what forms, Arthur?
Vertex and standard.
Yeah. Vertex and standard. Okay. In standard form, what is the quadratic notation in standard form? In standard form, Dave.
Isn't it ax squared plus bx plus c?
Good. And in vertex form, what is it? What is in vertex form?
y, or no, f of x equals a times x minus r1 times x minus r2.
That's intercept form. We'll do that over here. Hold off.
Oh,
You want to finish it now that you see?
no.
X minus h worth?
A times 20 x minus h in parentheses squared plus k.
Good. Nice classes, Worth. Those new?
Yeah, they are.
All right. Looking good. Right? I like classes. I'm a fan. All right, cool. So we got those two forms from 7-6. Now, 7-7, Francis, help us out. What was 7-7 form?
Oh. f of x equals a times x minus r1 times x minus r2.
Yeah. X minus R1, X minus R2. I'm running out of room there. Okay, X minus R1, X minus R2. That is called intercept form or root form or factored form. Any of the above are fine. There's no real name for it, but this is very useful. Now, in 7-6, we also talked about maxes and mins and what they are. So can somebody explain what they are and when you know whether you have a max versus a min? What are they and when do you know? Come in.
Well, the map, it's the vertex.
Okay, it's the vertex, very good.
And you know when you have a max or a min according to the graphs.
So a max, what would the graph look like if we had a max?
It would look like this.
Yep,
It would go down.
opening down. And what about a min?
Up and up.
Okay, opening up. Now, as Tori May said, the vertex itself is the point that is the max or the min. What else did we talk about with maxes and mins? There were some other little factors, little things that I mentioned.
The y value is restriction.
The y value or the range is restricted. Good. The range of a function is always restricted for quadratics based on the max or the min. So if this were my graph, and let's say this point was 3, 4, what would my range be for that graph? The domain is all real numbers. We made that statement many times now, because this goes on forever, left and right. But it doesn't go any higher than what value? 4. So the range is y.
Is less than or equal to 4.
Very good. There's our range. Okay. What about when we have a min? Say the min is over here. Let's say the graph looks like this now. And let's say that this coordinate is -4, -6. -4, -6. What would the range be on the graph on the right-hand side? Somebody else, come on. Use the left-hand side to assist you. This was the range over here. How does that differ over here on this graph? Chris?
Y is greater than or equal to -6.
Perfect, Chris. Okay, why'd you say greater than this time, Chris?
Because it opens upwards, so it's all greater than.
Perfect. It opens up. That's exactly right. When it opens up, it's everything greater than the minimum value. Well, the minimum value is -6. Over here, the maximum value was 4. It was everything lower than 4. What else about mins and maxes? We talked about location versus value. What is the difference? The word location means something. The word value means something else.
Is the value the y and the location is the x?
Good. So just write this here. Write it like that. Okay, to remind yourself. It's always location, value. So if somebody says the value of the maximum of this function is 7, that means that the y-coordinate of the max is 7. You may not know the location. You may know the roots. And you should know that the location of the max or min is what with regards to the roots?
Between like halfway.
The midpoint or halfway between, exactly. So if you know the roots are on this side, say the roots are 2 and 8, halfway between 2 and 8 is 5, right? So the x-coordinate would be 5. And then the y value is whatever you're told or whatever's given. So location and value. Let's see. That's the gist of 7-6. There were some other problems that we looked at, obviously. And we looked at transforming these equations. What is h and k again? To reiterate, what is h and k? Dave?
H is horizontal shift and K vertical shift.
Yeah. So remember, h comma k is our vertex or horizontal and vertical shift. Now let's look at standard form for a little while. Okay, I'm going to go to the next slide because I'm going crazy with room here. All right. Let's look at standard form. In standard form, we have A, B, and C. Let's discuss their significances. Okay? At standard form here. Who can tell me something about this? Anything about this form that you remember from class? Anything about this form that you remember from class? Can't be the same people all the time, guys. Come on. You don't remember anything about this at all? Like, what about C? What about the B value, the A value, or negative B over 2A, or different things like that? Austin, give me something. C is the y-intercept. Good. Remember that the coordinate 0, comma C is always the y-intercept. Because the way you find the y-intercept is by setting x equal to 0. If I cross this out, and I cross this out by setting x to 0, I'm just left with y equals c. That is the y-intercept. Next. What else? What else? What is this? What is this? Axis of symmetry. This is your axis of symmetry. Okay? Axis of symmetry. Now, how is that related to vertex form? What's the axis of symmetry in vertex form? In vertex form. X equals h, yeah. Okay? So this is your axis of symmetry in standard form. Here's your y-intercept. Remember that the axis of symmetry in vertex form is just x equals h. X equals h. And then A again indicates what? What does the A value tell us about the graph? Natalie?
If it's wide or narrow.
Exactly right. It's width or narrowness, and if it opens up or down. Okay? So if it opens down, A is negative. If it opens up, A is positive, right? The width part. What about the width part?
It's less than 1 wider.
Yeah, if it's...
Greater than 1 square.
Yeah, and we're looking at the absolute value there, right? So a number like negative 4x squared, well, 4 is bigger than 1. Not forget the negative part. So it'll surely open down, but since it's a 4, it's going to be a narrow graph. If it was like 1/2 or 1/3 or 0.7 or whatever, it would be a wider graph. When you do graph these functions, which you will have to do that, I'm telling you now, you need to follow directions. So many of you lost points in the last test because it said things like identify the intercepts on the graph, label your graph. You need to label axes. You need to put increments. I can't imagine how you're still forgetting that stuff. X, Y, label it. Label your increments as 1, 2, 3, 1, 2, 3, or at least put a 1 on each spot. That's fine. Because you may go by 4s along the y-axis because maybe your maximum is at a coordinate like 3, 20, right? So you might go by 4s along the y-axis and only 1s along the x-axis. Or you may go by 3s on the x-axis because your x-intercepts are out at like negative 12 and 7. So it depends on what the graph is. So you need to specify. I am not assuming you're going by 1s. Put something there. Put the first increment at least, and I'll know the rest. Does that make sense? So put a 3 there to show that you're going by 3s. And the y-axis is going by 1s, just put a little 1 on the first notch. If you know that your graph is going to be in the first quadrant, make the graph look that way. So for example, let's say I know, here's the equation. Okay? The vertex is h comma k. H is 3 and k is 5. Remember, the generic form is this. Okay? So look, k is replaced with a 5 and h is replaced with a 3. So that is clearly my vertex in this stone.
Should that be -3?
But look at the equation, Hannah. Look up here. It's generic form. It's x minus h, and this is x minus 3. So what has taken the place of h? 3. What has taken the place of k? 5. Okay? And it's odd because one of them is negative, one is positive. So you have to look at the equation and see what's happening. So for the h value, it's really whatever the opposite of this is here. You see, that looks like a -3, it's a positive. For the k, it's whatever you actually see there. So if that's the vertex, and the graph is opening up or down? Up. Why is it up, Ida? Because A is positive right here. So my vertex is in the first quadrant, and it's opening up. So everything's going to be in the first quadrant. So when you have a grid on your test, I'm going to give you that grid. Please only draw the first axis. You can draw like this, but specifically open up the first axis. Because look, 1, 2, 3, 1, 2, 3, 4, 5. There's my vertex, and it's only opening up. So we know that I'm not going to be using the other quadrants. So assist yourself when graphing. Okay, help yourself out. What can you do to check that you're right?
Calculator.
Yeah, check on your calculator at least. Okay, if you just put a graph with no words, obviously you're getting no credit. So don't just type it in and draw your graph. Show all your work, show all your labeling. But you can check on a calculator. You can check on a calculator. In 7.7, we talked about intercept form, but then we also talked about maximization and minimization techniques. Intercept form told us the following. So if you're given a problem where you're told the x-intercepts are 7 and -4, what do you start right away doing with your function? The x-intercepts are +7 and -4. What do you do right away, Austin?
R1 and R2.
Good. Okay. So x is, we said again, +7. So this is a +7 going there. The negative sign just comes from the actual form. And then we said -4. So it's -4. Okay. So again, make sure that you remember that the negative signs right here and here are coming from the generic form, not the root itself. This root is +7. This root is -4. Okay, now clearly this is really just x plus 4. Now what else do I need to finish off a problem like this? Because I don't have enough information just yet. I need something else. What else might I need? A. How do I get A? What other piece of information might the problem give me to then discover what A is, or figure out or determine what the value of A is? Think back to these problems. What other piece of info did the problem give you? We need something else, and you would be given something else in the test. I had to finish it off. A point, exactly. Look at the equation right now. You have x, you have a, and you have f of x or y. To get a, you would need to know what x and y are so that a is the only variable left. It's the only way you can solve one equation for one variable is by knowing what x is and what f of x is. Well, x and f of x are a point, really. So let's say that you're told the maximum value on this graph is 6. What does that tell you about a point that you have? Part of that point, obviously. If the maximum value is 6, Natalie. Okay, the y is 6. Perfect. What else do you now know based on the other information?
We know that A is negative.
A is definitely going to be negative. Why is A going to be negative? Because this is A?
Should affect the word, but concave down.
Concave down. We said it was a max. Didn't I say this was a max value? So already Worth knows that it's going to open down if there's a max. So A has got to be negative as an answer. got to be negative. Now, take a look here. What is the x-coordinate of this point? And we just made this statement. Arthur answered the question a little while ago. I know the roots, so how do I find the x-coordinate of the maximum? If you don't remember, just sketch in your mind what's going on. Take a look. Everybody look up there. The first root was 7. That's out here. The other root was -4. That's over here. The maximum occurs up at 6. That's somewhere along here, up at 6. Well, the maximum's got to be in the between, right? Because we know that the graph always looks like that from the max down. So what do we know about this x-coordinate here? How can we determine its value? How can we determine the x value?
You can count like between 7 and -4.
Yeah. So find the what? What's the word for that?
The middle.
The middle, or the midpoint. How do you find the midpoint very easily along one axis? Anybody know? Add them up, divide by 2. Find the average. So add your roots up. What's 7 plus -4? 3. 3 divided by 2 is? And take a look where that lies. Right to the right of the axis. So it's 1.5. So there's the coordinate. So maybe you're only given a max or a min value, and you have to find the location by averaging the roots. You can write that down, please. The location of the vertex is the average of the roots, or the midpoint of the roots. Okay, that always will work out that way if you know the roots. Now, what would I do at that point to solve for A? We're going to leave this problem at this point once we do this. What would I do at that point now to solve for A? Plug it in, right? That's all you can do at the point. Okay, then solve for A and write your final answer like this, right here. I'm circling it, but with whatever you get for A, plug that number in there. Dave?
And above they want us to put it in standard form.
I'm not going to have you do that. You mean like FOIL it out and get it in standard? No, root form is just as good.
Okay.
If it was like a two-part question where then I wanted you to put it in standard form and find the axis symmetry using standard form to prove that it actually is 1.5, that could be like a follow-up question, but I'm not going to just make you put it in standard form as an answer. Okay, but only if it would be a follow-up. All right, we also did something with the sum of roots and the product of roots. Look at your notes from 7-7, because this was something that confused some people, and there was some trouble on these parts. Okay, if you're given roots and only roots, using the sum and product of roots, you can come up with a possible function. So let's take a look at an example of that. And this is really interesting when you have imaginary roots. Okay, imaginary roots are the ones that are really more interesting. Because if you have regular roots, you could use intercept. You wouldn't know what the a value is, but you could technically pick an a value. For this part, we're going to say that the roots are 2 plus I. Let's just say 2 plus or minus I. Okay, those are the roots of this function. So this function is clearly floating above the axis, or floating below the axis, but there are no x-intercepts here. Why are there no x-intercepts if these are the roots of the function, or the roots, or the zeros of the function? Why do we know there's no x-intercepts based on these zeros here?
Because
In order to have x-intercepts, the zeros have to be what? Real numbers. This is an imaginary quantity. So that means that this is a graph that's looking like this, or maybe like this, or like this, or like this. But there's no x-intercepts on this graph. Okay? So when you come up with your function at the end, you could plug that function in that you get in your calculator and just look at it and make sure that there's no x-intercepts. Just to give you another feeling of confidence that you got the right answer. Do you follow what I'm saying? It's a way to check your work. Again, there are simple checks. When I say check, it doesn't mean you have to redo the problem. It means doing a sanity check. Why did I get a negative a value? Because it opens down. Why did I get a positive? It opens up, etc., etc. So those are my roots. Now, based on sum of roots and product of roots, how can I come up with an equation for this scenario? Give me one piece, go ahead.
Well, to get C, it's the roots time multiplied by each other, so it's 2 plus
can just make A 1.
Yeah, we said let A be 1 for now. That was the statement. Let's FOIL this out first, though.
And then you get 4, and then
The middle terms, what happens?
they cancel.
Remember, it's 2i and a negative 2i in the middle. Whenever there's complex conjugates, they cancel.
And then you get negative I squared, which is just positive 1, right?
That's correct. Minus negative 1, which is a positive 1. So this is just what number?
C,
And it equals what number?
it equals 5.
So C is 5 for now. Remember, it's really C over A, as Arthur mentioned, but we let A equal 1 here. That's a C, by the way, that's a C. We always say let A equal 1. So already we know that our function looks like this. I'm letting A equal 1. We don't know what B is. And then at the end we have a plus 5. Okay, but we have to figure out what B is now. What did we know about the sum of roots? The sum of roots is not equal to C over A like the product was. The sum of the roots equals, Natalie? Negative B over A. Good, I'm glad you said the negative. Okay, a lot of people forget the negative part there. So again, we let A equal 1, and we sum these roots together. Let's sum them together. So negative B over A equals 2 plus I plus 2 minus I. It looks the same except this plus sign in the middle. What happens always? Always, 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 always when you have conjugates. Whether they're binomial conjugates with like 2 plus or minus radical 3, or complex conjugates with 2 plus or minus I. What's always going to happen when you add them?
You'll get different squares.
That's when you multiply. Yes, when you multiply. When you add them, though.
You'll get 4.
Yeah, you just get the real part, or the rational part, or whatever this beginning part is, always. Because it's a positive I and a negative I added together. If this was 2 plus radical 3, 2 minus radical 3, the same occurrence would happen. So B, or negative B, is 4. Again, take a look at this. Negative B is 4 in this problem, not B. So what is B? And B is negative 4. Again, if negative B over A, where A is 1, if negative B is 4, then B has to be negative 4. So our function becomes this up here, but with the negative 4x there. Okay, that's my function. Do I need to multiply this out if it says anything? Not multiply it out. Multiply by any constant? What was the one condition I gave you in class with the example? I said it has to have blank coefficients. Integral or integer values. Integral is the word though. Integer value coefficients. Are these coefficients integers? So even if it said that in the directions, you don't need to multiply by anything. But this is one possible function with roots, or really zeros, of 2 plus or minus I. If you double everything and make it 2x squared minus 8x plus 10, the roots are still 2 plus or minus radical I. You know what you're doing now? Here's what you're doing when you double it. So let's say this is the graph. Let's say, well, it's hard to illustrate this with imaginary roots. Because imagine that the roots are real for a second. I know they're imaginary. Make believe they're real because it will be much more obvious. Say this is your graph and say that the roots we started with were real, okay? And if we doubled all of these values, all that would happen was it would increase the steepness of the graph. So it would make the graph now look like this. But it would still go through the same roots. Okay, if I tripled the values here, it would again make it steeper. Okay, that's all that's doing. It's just changing, stretching the graph vertically. So whenever you get an answer, that answer is one of the possible answers with the roots that were given to you. We happen to have imaginary roots, so this is not what our graph would look like, but it's easy to illustrate with real roots. Okay? Hannah?
How do you form a question answer?
Like that?
Yeah.
Given the roots, or given the zeros of a function are the following, determine a function that has these roots and has integral coefficients. I mean, same way you had on the notes. There's not much more to it, or not many ways to say it. Okay? All right. That's part part of 7.7. Let's finish up 7.7 so we can get to the other stuff. Okay, let's finish it up. The easy problem was the one we did with the cost function. So I'm not going to go over that one. But the tougher ones were the ones with like area. We wanted to maximize area given a certain constraint. Okay, with the sides and stuff, yeah. So let's say that a problem tells you that a fence is used to make a stable in a barn. So here's the barn, and the fence used is adjacent to the barn, but there's 4 stables. They need to be split by that same fencing. Okay? So here's the stable behind the barn. Here's the barn house, bird's eye view. Okay? So in the stable, here's the 4 horses hanging out, eating their hay. So the perimeter, or the amount of fencing that you're told in this problem, is 100 feet of fencing. And the question asked of you is to determine the dimensions, okay, that can maximize the given area. Now, let's hope our dimensions are realistic for horses. I don't know if they're going to be, but I just made up the problem on a whim. But let's assume that these horses could be any size. Although that would be another constraint, right? Like the dimensions of these individual stables would have to be greater than a certain value. With multiple constraints, you can solve this also, but then you get into what's called Lagrangian mechanics, which is a type of engineering, actually. So we're going to say for now that we just have a perimeter constraint, and we have a certain amount of fencing given, okay? So in this, you want to give us a starting point?
I mean, like, isn't the length just like half of the available?
That's when there was just, remember, 3 sides. That was the rule to remember, only with 3 sides. Not, look how many individual barriers are going to be in here. These are all fencing, don't forget.
Oh, I thought like the blue box was the...
Oh, no. The red, yeah. His point is good. Remember the point he makes? If there was only 3 sides, we talked about how these ended up being half of this. So it was like 50, 25, 25. And that always works out that way. Now, when there's more stables or more divisions, then I'm going to do that for sure. So you can't just get the answer, just by memorizing. Dave, give me a starting point.
Well, what variables should we use?
You pick.
X and Y.
All right.
So you can do 4x plus y would be 100 feet.
Not 4x.
Oh. Alright.
Yeah. It's 5 of them, right? And this is our, I'm going to put in parentheses, constraint. What does that word mean again? It's a restriction. It's a material or a resource, God bless you. A restriction on your resources. We want to maximize the area. What is the area of the shape of this stable? What is the area formula for this shape? Everybody, what is the area? X times Y or LW, okay? In this case, we'll say XY, because those are our dimensions. All right, I cannot write this as a function, A as a function of X or Y, because they're both there. So what do I need to do in the constraint? Who remembers what I need to do in the constraint function? What should I do there, Chris? Yeah, which is easier to isolate, clearly. Yeah, Y is much easier to isolate. So solve for Y. Y is 100 minus 5X. Okay, please solve for the variable that has no coefficient. It's so much easier for you. Please don't solve for X here. That would be so much more work. You could get the right answer, but it'd be messy. So I solved for Y, so I'm going to replace that right here. Now I can do this. I'm going to erase A and write A of X to show that area is now a function of X. Like F of X or G of X. It's now A of X. And we want to determine the maximum value of the area. So this curve is clearly going to open down because it's a maximum. So it's going to be somewhere over here. I know that this is A of X and this is X. Okay, look at my independent variables X and my dependent variables A of X. So what does X represent again in this problem? The what of the bar of the stables? Or the rectangle, the what?
The 5 equal fences.
Yeah, those 5 equal dividers, the length of those dividers. Or you could say like the shorter side of the big rectangle, whatever, the width. But in this case, yeah, the dividers is X. So X has got to be positive, agreed? X has to be positive, the answer you get. Now, we want to know when the area is at a max. When the area is at a max, we're right here. That's where we are. And this location occurs along the axis of symmetry. So we need to find the axis of symmetry, or simply find the vertex. But to find the vertex, you first find the axis of symmetry to get x, and you plug that back in to get a of x. Okay, so let's do that. This function is actually quite simple because of the way it's written. I'm going to write it in standard form so that I remember what a and b are. I know now that I'm right so far because look at my a value. Notice the a value is negative here. A value is negative because the graph is opening down. So the axis of symmetry is negative b over 2a. So negative 100 over 2 times negative 5. And look at that. The axis of symmetry is positive, like we said it would be. Because this is the length, or the divider length, in the stable. So negative 100 over negative 10 is positive 10. So this location is 10. Location. Location. The value is what we are determining next. The location is great. That's awesome. That tells me that in this barn, all these dimensions are 10. If those are all 10, what is this big dimension along the bottom? 50. So Arthur, you were kind of along the right track. See that? Remember you said this is going to be half of it? It still is. But don't forget to split those up amongst them. And that also will always work out. So if you had 3 dividers, and then thus you would have 4 of these, right? Here there's 3 dividers, sorry. Let's say you had 4 fences like this. It would be 12 and a half, 12 and a half, 12 and a half, 12 and a half. If you had 3 fences, it would be 16 2/3, 16 2/3, 16 2/3, and 50 there. Okay, so you would split this amongst. This is always going to be half of it. Now, you know the 10 values, you know the 50. What is the area now? Just multiply length times width if you'd like to in the diagram. What do you get? 500. It's the same thing as doing this. It's really important that you notice what I'm going to say next. So, either I could just simply plug in and write my diagram out and do 10 times 50 and get 500. Or I could say the area evaluated when x is 10. That'll give me the maximum area. This on the left is negative 500. This is 1,000. 1,000 and negative 500 is 500. And what are my units? If it's area, feet squared. Okay, so at the end of these problems, you can either run a of 10 through the function because you got 10 to be your x value, and this is really giving you y value of the vertex, or you can put it back in the diagram and just multiply length times width. Either way is fine. Either way is fine. But let's remind ourselves that what we've really done is we found this vertex. Okay, so this here is what we've just done. 10, 500. So those dividers are 10 feet each. The area is 500. All right. Fractions. Fractions that involve variables. What do you do to add and subtract fractions? Excuse me. You need a common denominator. So let's say we have 2 over x squared plus 4x minus 3x over x squared minus 16. How do I start to find a common denominator in a problem like this? Because it looks very difficult. It looks real difficult. Georgia, what should I do?
Find the common denominator, so you have to find the little LCM of the 2.
Okay, but to do that, what's my first step?
Factor out.
Good. So what do you got?
So you have x times x plus 4.
And over here?
X plus 4 times x minus 4.
Good. Then somebody else, what question do you ask yourself at this point? What question, Liam, do you ask yourself? What's missing? Well, here x minus 4 is missing. And here x minus 4 is missing. Okay, if it's on the bottom, it's got to be on the top. And on the right-hand side, x is missing. So we'll put an x over here also. Now, my denominators are the same now. So I can write this all as one denominator. The numerator, remember, I have to distribute this. I get 2x minus 8 minus 3x squared. Right? 3x times x is 3x squared. I leave the denominator in factored form. Why is that? Why do I leave that denominator in factored form, Dave?
Because if you factor the numerator, you might be able to cancel out.
Correct. You may be able to factor the numerator and cancel. Okay? Can you run this through your program real quick, Dave? Tell me what you get for roots, and then we can determine if it's factorable or not. If the roots turn out to be rational, then this equation is factorable. If they come out to be irrational, it's not factorable. So we got 3, 2, negative 8.
Well, you get 1.3 repeating negative 2.
And negative 2. So it is factorable, which means that the roots are x plus 2. You said 1.3 repeating?
Yeah.
And 3x minus 4. The reason I knew that is he said that one of the roots was, you said negative 2?
Yeah.
If a root is negative 2, then one of the factors has to be positive 2. We'll talk about this in chapter 8. This is one of our theorems. But this is an easy way to figure out your factors. When he told me that, then he told me that the other root was 1 1/3. Well, if I solve this 3x minus 4, you get 4 over 3, right? Add the 4 over and divide by 3. 4 over 3 is 1 1/3. That's how I knew those were the factors. But anyway, does that matter in this problem right now? Why doesn't it really matter? Even though we were able to factor it, why doesn't it matter? Nothing cancels. You can write it that way, and that's good. You should check always, but it turned out to not cancel there. Okay? That's 5-6. 5-7 is similar to that because you're finding an LCD. So 5-7, let's... Okay, so take a look at all these now. And again, like last time, what I want you to do is to factor them. And then say what's missing in all of them. But you're not going to write them on here this time. Okay, you're not going to write them on here. All you're going to do is factor everything. What's the only thing that can be factored in this problem? The only thing that can be factored, Austin?
X plus 4.
Which is what?
X plus 1, X plus 4.
Convenient, huh? I think not. Okay, I did that on purpose, obviously. X plus 4, X plus 1. Now, take a look. List all of the factors of your denominators. All of the factors, list them. And that is your LCD. Your LCD is just listing them. So what's one of the factors? One of them. X. It's right here. Under the 4x, right? So one of the factors has to be X. So we start with X as the first part. What's another one of the factors that you see somewhere? Worth? X plus 4. It's here and it's here. It only occurs once at most in any denominator, so we only have to write it once. And what else? What's the last part? Anybody? X plus 1. Good. That occurs once here and once here, so still, it only occurs once at most. So that means that the third part of my LCD is X plus 1. Now, I take the fraction I have here and I multiply the top and bottom by that quantity. Okay, I'm going to cross that off. Make this giant thing of parentheses now. Okay? So that's what's going on in this problem. We take the LCD that we determined and multiply it. Why is that so convenient? Is today B-Day? Quick. Okay, we got like a minute. Why is that so convenient? What happens when you distribute it out? A lot of things cancel. This X plus 4, give me like 3 seconds, cancels with this one. Leaving behind here 3x, x plus 1. 3x, x plus 1. Here, x cancels with x. Leaving behind 4x from here, and then these two factors. X plus 4, x plus 1, and so forth and so on, and it continues in the bottom. Okay? Make sure you look at Moodle on the documents and handouts. I'll try and get the review document up by the end of today. Feel free to come by during activities. Remember, there are 2 more sections still, the ones we recently did. Make sure you look at those. Problem sets tomorrow.